Hey everyone, this is Coach Hare. I hope everyone is doing well. Today we're going to be talking about arithmetic and geometric sequences. For those of you that are Algebra 2 students, this is Chapter 8 in your textbook, Arithmetic and Geometric Sequences. So let's jump right into it. A sequence is an ordered list of numbers. An example of that would be your locker combination. For example, 5, 12, and 7, if this was your locker combination. Then obviously you'd have to put the 5 in first, and then the 12, and then the 7. Since order is involved, we call this a sequence. So by definition, a sequence is an ordered list of numbers. Now there's different types of sequences. A finite sequence just basically means that it ends, like your locker combination. It started with the number 5, but it ends with the number 7. So therefore, a finite sequence is a limited number of terms whose domain is the finite set 1, 2, 3 all the way to n, which was whatever your last number is. The values of each term is the range. So think about it this way. If you take a look at your locker combination again, 5, 12, and 7, your domain value would be 1, that would be your first term, but its value would be 5. So your domain is 1, its value is 5. Your second term, because of order, because it's a sequence, would have a value of 12. Your third term would have a value of 7. So if you looked at this like a domain and a range, an input and an output, the order of your terms would be your domain, and your values would be your range. Now an infinite sequence, well, infinite just means it goes on forever. So therefore, this would be a locker combination that you would never be able to open. It'd be 5, 12, and 7, and then a whole bunch of other numbers that would go on and on and on. We'll get into the difference between finite and infinite sequences a little bit more later. So we need to think about, why do we need to study sequencing? Well, first and foremost, there's patterns. Patterns, if we can figure them out, we'd be able to calculate other terms' values. So for example, if we could identify a pattern, back to your locker combination, if someone could figure out a pattern to your locker combination, they wouldn't need all the numbers because they'd be able to calculate what the other numbers are from the pattern. If we can identify patterns, then we can calculate term values, but more importantly, we can come up with a general rule for or equation for that sequence. So let's take a look at a few examples. Here you have the sequence 3, 5, 7, 9. What do you think the other numbers would be that would fit into the blanks? Hopefully you were able to realize that the difference between 3 and 5 is 2, 5 and 7 is 2, 7 and 9 is 2. So if we increase 2 or add 2 to the 9, we get 11. And then we add 2 more, we get 13. And then if we add 2 more, we get 15. So by identifying the pattern between the numbers, we're able to extend this sequence and predict pretty reasonably what we think the values are going to be. Take a look at example B. What do you think the 3 blanks values would be? Hopefully you would be able to see that there's increasing by 5. So my next value would be 21. 21 plus 5 is 26. 26 plus 5 is 31. Take a look at example C. C is not as obvious as A and B. We're not just increasing values. But there's something else going on there. Can you find the pattern and predict what the next 3 values would be? This is a tough one, and it's also a famous one. This is called Fibonacci sequence. In this sequence, you notice that the sum of the previous two equals the third term. So therefore 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8 equals 13. If we continued with this pattern, we would come up with 8 plus 13, which would be 21. 13 plus 21 is 34. And 21 plus 34 is 55. Once again, we're still able to identify a pattern and use that to extend the sequence and predict the values. Take a look at D. Can you predict the next three values from this sequence? This one's a little bit harder, because what's happening is, if I look at the change from 3 to 8, I notice it's 5. From 8 to 15, I notice it's 7. And from 15 to 24, I know that it's 9. Now this might not be the approach that you use to come up with it, but it does look like a pattern is emerging. And so my next change should be 11, and then 13, and then 15. If I add those numbers to the terms values that I already have, I end up with 35, 48, and 63. Now back to the top. We've identified the patterns, and we use those to extend our sequences or calculate term values. But what about the general rule? Meaning, is there a rule that we could come up with, for example A, that would explain every single value that we would get, no matter which term we were looking for? And there is an answer to that. Using sequence notation, I can say that A sub n represents the number of the term. For example, again, the number 3 would be term number 1, the number 5 would be term number 2, the number 7 would be term number 3, the number 9 would be term number 4, and so forth and so on, until I get all the way out here to term number 7. So I have 7 terms, but they have different values. The value of my 7th term is 15. If I wanted to find any term in this sequence, for example, if this went on further, I could say that any term in this sequence, denoted by A sub n, is equal to 2 times n plus 1. Let's see if that works. If I let n equal 1, and I substitute 1n, 2 times 1 is 2 plus 1 is equal to 3. As you can see, when I took an n of 1, my domain value of 1, and put it into my general form of this equation, I ended up with a value of 3. Would that also work with the term 7? Why don't you check and see? You would say that the 7th term is equal to 2 times 7 plus 1. And as you can see, it does work out. So why do we study sequences? We study them to find patterns so that we can calculate term values, and eventually, as we go further into this chapter, we'll learn how to write general rules or equations for our sequences. There are many sequences that we're going to study. However, what we're going to focus most of our attention on is an arithmetic sequence or a geometric sequence. Now, an arithmetic sequence is very simple to identify. It simply has a common difference. So you need to associate an arithmetic sequence with a common difference, and it has a variable d. Here's your formal definition. An arithmetic sequence is the difference of consecutive terms, and that difference is constant. So for example, if I went back to one of the examples I used earlier, 3, 7, 11, and 15, 3 being the value of my first term, 7 the value of my second term, and I wanted to determine if in fact this was an arithmetic sequence. What I could do is use the formula d is equal to the second term minus the first term. What is the value of the second term? It's 7 minus 3. 7 minus 3 equals 4. If I took a look at the next two terms, and this time took the value of the third term, which is 11, and subtracted it from 7, I would still get a 4. And I think you can identify that this sequence is increasing by 4. Since it is constantly increasing by 4, we can say that this is, in fact, an arithmetic sequence. Now, what is a geometric sequence? A geometric sequence, by definition, doesn't have a common difference, but has a common ratio. We use the variable r. A geometric sequence is the ratio of any term to the previous term is constant. Now this one can be a little bit more difficult, but here's a simple example. If I give you the numbers 2, 4, 8, and 16, again my first term value is 2, my second term's value is 4. If I want to determine if this was truly a geometric sequence, what I would do is take the formula that r is equal to the second term divided by the first. Now it's very important that you keep these formulas in the correct order. You make sure that you take the second term divided by the first. Otherwise, you'll end up with values that are misleading. The value of the second term is 4 divided by 2. That gives me a constant ratio of 2. If I come over here and take 8 and divide it by 4, I also get 2, as you can see. And 16 and divide it by 8, I also get 2. Since my ratio is constant for all of my terms, we can say that this is in fact a geometric sequence. So again, if it's arithmetic, it has a common difference. We want to make sure our formula is accurate, meaning we want our second term minus our first term. And if it is a geometric sequence, then it has a common ratio. And when we calculate that, we want our second term divided by our first term. On your assessments, you'll be asked to determine if it's arithmetic, geometric, or neither. Again, if it's arithmetic, they'll ask you to find the common difference. If it's geometric, they'll ask you to find the common ratio. Take a look at A. Example A. What would you say this is? Okay, what did you end up with? Here's my first term, here's my second term, my third term, my fourth term, and my fifth term. If I want to calculate my ratio, I'm going to take the second term divided by the first term, which gives me 64 divided by 256. That's 1/4. You see, if you would have switched these around, you would have implied that we were multiplying by 4, when you can obviously see that in fact we're dividing by 4 as we move from 256 to 64. What about the next two terms? If I take the third term and divide it by the second term, I end up with 16 divided by 64, which is again 1/4. And as you can see, even with the fifth term and the fourth term, this would be 1 divided by 4. So in essence, this is a geometric sequence. What about example B? Once again, if I look at my terms, with the value of my first term being -1, the value of my second term being 2, if I take the ratio, because I think it's geometric, the reason why I think it's geometric is that I can see that 2 times 2 is 4 times 2 is 8 times 2 is 16. But when I go ahead and formally do the calculation, I end up with a -2. Now, do I have to do every single term? No. I can take a look at ones that I have questions about. Like, for example, how about -16 divided by 8? Well, that's also going to give me -2. So this is also a geometric sequence. However, if r is negative, we call this an alternating geometric sequence. Alternating because it's going back and forth from negative to positive, positive to negative, negative to positive. Take a look at example C. What do you think example C represents? I don't think it would take you much time to realize this is not geometric, because it's impossible for me to multiply 17 and come up with a consistent ratio for each one of these numbers. But it does look like it's decreasing, and it's decreasing by a common difference. But here's where I have to be careful. You see, my first term is value is 17, my second term's value is 14. When I find the common difference, I end up with 14 minus 17, which is -3. This is why I was telling you earlier to be careful about how you add and subtract and how you divide. And it's easy to see that in fact this is decreasing by 3, and that's the reason for the negative. So since this has a common difference of 3, we would say that this is an arithmetic sequence. Take a look at example D. I have some concerns about example D, and here they are. When I look at, for example, the first two terms, I notice that when I take the second term and divide it by the first term, I end up with a ratio of 2. However, when I take the fourth term, and you may be wondering, why did I use the fourth term? You can use any pair. But what I notice is I get 30 divided by 20, which is 3/2. These two don't match. I ended up with a ratio of 2 and a ratio of 3/2. So this is neither geometric or arithmetic. Let's recap. If it's geometric, it should have a consistent ratio. In our first example, we calculated it as 1/4. So my R value was 1/4, We were asked to determine if it's arithmetic or geometric. We did, and we found the R value to support that. In our second example, we were asked to determine if it was arithmetic or geometric. We determined that it was geometric, and its R value was 2. Since it was -2, we can call this an alternating geometric sequence because the values alternate back and forth from right to left, from negative to positive, and from positive to negative. In example 3, we noticed that our values were decreasing by a constant value of -3. Since there was a common difference of -3, we said that we had an arithmetic sequence. In example D, we noticed that there wasn't any consistency. We're adding 6, adding 8, adding 10, adding 12. Sure, this is a sequence, but it is not arithmetic or geometric. If we are able to determine that something is arithmetic or geometric, then we have a general rule that we'll be using in our next lesson. An arithmetic sequence, we can calculate any term in that sequence if we know the first term, what term we're looking for, and our common difference. Likewise, in a geometric sequence, if we know it's geometric, we can calculate any term if we know the first term, the common ratio, and what term we're looking for. Again, we'll be discussing this more in the lessons to come. There's one other way that we can illustrate sequences, and that's called a recursive sequence. Now, a recursive sequence basically tells us that they're going to give us an initial value, the beginning value, and then they're going to give us a recursive equation. Now, if I was in the classroom, people would be asking, will we always get this? The answer is yes. You will always get an initial term, and then you'll get an equation to support the rest of your terms. Now, the joke I like to tell here is that it recurves. So if you watch carefully, what I'm going to do, it's really quite simple to figure out how to find terms using a recursive equation. A sub 1, or my first term, is 7. So I'm simply going to say that the first term's value is 7. Now, what do you think this second equation is saying here? It's telling us how the rest of the terms relate to the first term. So for example, if n equals 2, then this would be 2 minus 1. What is 2 minus 1? It's 1. But we already know the value of our first term. So therefore, if we took a sub n minus 1 plus 3, we already know this value. So we're going to simply plug this in, end up with 7 plus 3, which is 10. And then we just continue this process. So in essence, we need to figure out the previous value in order to know what the next value is going to be. So for example, a sub n minus 1 plus 3, 2 minus 1, or excuse me, 3 minus 1, because we're looking for the third term. 3 minus 1 is 2. We know what the value of the second term is, so we're going to simply substitute it in. And my third value is 13. What about a sub 4, or my fourth term? Well, my previous term is 13, so I'm simply going to substitute that in, plus 3, and I'm going to get 16. So I take again, I'm going to substitute the 13 in, and I'm going to add the 3 and get 16. Now what about this fifth term? Well, again, if I use my original formula, a to n minus 1 plus 3, well, n is 5. What's 5 minus 1? It's 4. The value of my fourth term is 16. So I'm simply going to take the 16, substitute it in, 16 plus 3 is equal to 19. So the first 5 terms of this sequence would be 7, 10, 13, 16, and 19. I think it's easy to see that these are increasing by 3. So we could even go ahead and conclude that this is an arithmetic sequence. Why don't you try B? The first term is 5, and the equation that relates the rest of your terms is a sub n is equal to a sub n minus 1 minus 2. See if you can figure out what the next values would be.